Hi EMC, I am Patricia Florissi, Americas and EMEA CTO. Most importantly, I am a proud EMCer just like you. Together, we have a clear mission to demystifying Hadoop. In reality, the ideas behind Hadoop are very simple. The only thing is that we all need to know what these simple ideas are. By understanding the simple ideas behind Hadoop, you will be able to uncover a whole new way of thinking about big data analytics, be able to understand how EMC is uniquely positioned to accelerate adoption of Hadoop worldwide, and to take a thought leadership role in engaging the world on adopting Hadoop for big data analytics. When learning about Hadoop, it is very important to have the right architectural context in mind. Hadoop was designed for cluster architectures, which we simplified in another Big Ideas video called Simplifying Cluster Architectures. So please take the time to view the Simplifying Cluster Architectures video to quickly review the design principles behind a cluster architecture. Having a good insight into how cluster architectures were designed is a prerequisite to gaining a better understanding of Hadoop. We hope you enjoy and benefit from this video and have fun. It is called Demystifying Hadoop. There are many misconceptions around Hadoop these days, creating a cloud that sometimes inhibits us from engaging in it for fear of getting tangled with all the complexity that, as we believe, for sure must follow. In great part, the myth around Hadoop may be a side effect of its name, which is new and whose meaning cannot be easily explained. So we decided to start demystifying Hadoop by simply explaining, well, what is in a name? Hadoop was created by Doug Cutton, who named his new project after his son's favorite toy, a stuffed elephant, for whom the boy had given a name he himself had made up. The elephant's name was Hadoop. So that was pretty fast, 30 seconds or so, and we have just demystified the first myth that the name Hadoop has some very deep meaning or stands for some acronym. Now that we understand the origin of Hadoop name, we are going to emphasize that Hadoop was not designed with the typical enterprise environment in mind. Hadoop was designed for a cluster architecture built out of commodity hardware. Trying to understand Hadoop concepts in the context of the wrong architecture design can, indeed, hurt our brains. It's important to remember that a cluster architecture is based on a set of very simple and basic components that can be available in the thousands or hundreds of thousands and can be easily assembled together. It all starts with a node consisting of a set of commodity processing cores and main memory attached to a set of commodity disks. Then a stack of nodes forms a rack, and a group of racks form a cluster, all connected via a high-speed network to enable fast exchange of information. Hadoop was designed to leverage the resources and architectural layout made available within a cluster architecture. So when thinking Hadoop, put your mind in the right context and think cluster architecture first. Now, before we dive deeper into the concepts and elements that make up Hadoop, we need to add one more layer of context to this discussion, which answers the eternal question of why. Why was Hadoop created? It is actually very simple. People were looking for a way to continuously index massive amounts of data. Specifically, the initial work was done by a little company called Google, who needed a way to index the entire World Wide Web every day. Needless to say, their investment has paid off. Doug Cutton got the inspiration for Hadoop after reading Google papers on the Google file system and Google's MapReduce, which described a design paradigm that used commodity hardware to effectively process massive amounts of data in a fraction of the time previously required. Why is that critical to us? Final why, I promise. Because 10 years later, just about all companies have their own big data challenge that no matter how hard they try, cannot be solved with traditional enterprise approach to analytics. And as a result of the breakthroughs made by Google and others who joined them early on, including Yahoo and Apache, today there is a fast-growing industry emerging inside of high-tech focused on helping achieve things never thought possible before. Facebook, for example, uses Hadoop for processing and analyzing data patterns across its 845 million users, almost 1/7 of the world's population worth of personal data. So what is it about Hadoop that enables this to happen? Well, first, it's that Hadoop was designed to enable applications to make the most out of a cluster architecture by addressing two key points. One, the layout of the data across the cluster, ensuring that data is evenly distributed, and two, the design of applications to benefit from data locality. And that brings us to Hadoop's two main mechanisms, the Hadoop Distributed File System and Hadoop MapReduce. The Hadoop Distributed File System is a file system to split, scattered, replicate, and manage data across the nodes in a cluster. MapReduce is a computational mechanism to execute an application in parallel by dividing it into tasks, collocating these tasks with parts of the data, collecting and redistributing intermediate results, and managing failures across all nodes in the cluster. We will first gain a better understanding of the Hadoop Distributed File System and then explore MapReduce. The Hadoop Distributed File System, like everything else in Hadoop, is based on very simple and uniform design principles. A file consists of equal-size file blocks, sized to be a multiple of the storage block size. In the Apache Hadoop Community Edition, for example, the file blocks are 64 megabytes, while the storage blocks are 512 kilobytes. Hadoop uses a file block as the unit used to distribute parts of a file across disks in nodes. Since cores and disks in a node and nodes in a rack can fail, the same file block can be stored on multiple nodes across the cluster. The number of copies can be configured, but by default is often set to 3. Hadoop file system is classified as a distributed file system because it manages the storage across a network of machines, and the files are distributed across several nodes in the same or different racks or clusters. Hadoop treats all nodes as data nodes, meaning that they can store data, but designates at least one node to be the name node. For each Hadoop file, the name node decides where each disk, each one of the copies of each one of the file blocks will reside, and keeps track of all that information in tables stored locally in its local disks. When a node fails, the name node identifies all the file blocks that have been affected, retrieves copies of these file blocks from other healthy nodes, finds new nodes to store another copy of them, stores these other copies there, and updates this information in its tables. When an application needs to read a file, it first connects to the name node to get the addresses for the disk blocks where the file blocks are, and the application can then read these blocks directly without going through the name node again. One of the common concerns about the Hadoop distributed file system is the fact that the name node can become a single point of failure. If the node where name node is fails, all the mapping information between file names and the address of their respective file blocks may be lost. And the new node needs to be designated as a name node with the same IP address of the name node that failed. In order to address this issue, Hadoop saves copies of the tables created by name node in other nodes in the cluster. In addition, some versions of Hadoop, especially Enterprise Edition ones, have other nodes serving as backup for the name node. Now that we have a good grasp on the Hadoop distributed file system, we will then explore the Hadoop MapReduce computational mechanism, which again, like everything else in Hadoop, is rooted around a small set of very simple concepts. As the name suggests, MapReduce sees a computational task as consisting of two phases, the mapper phase and the reduce phase, which are executed sequentially, first the mapper phase and then the reduce phase. During the mapper phase, all nodes will do the same computation, but against the part of the data set that is co-located in the node or closer to it. In other words, MapReduce uses the principle of data locality to increase performance and minimize information movement. It is important to note that because all the file blocks in the Hadoop distributed file system are of equal size, the mapper computation can be equally divided across the nodes. If the file blocks were not of equal size, the processing time would be dictated by the time it took to process the longest file block, while the other nodes would be idling. Consider the situation where you have a file that aggregates blog entries related to big data posted in the last 24 hours. The file has been stored in a cluster using the Hadoop distributed file system under the name of bigdata.txt, which divided the file into file blocks and stored at least 3 copies of each file block across the nodes in a 50-node cluster. In the example, you want to start analyzing this big data by first counting the number of times that Hadoop, Big Data, and GreenPlum have been mentioned. Assume you have a mapper function that takes as input the address of a file block and counts the number of times each one of these words appear. Each node participating in the mapper phase will then receive a pointer to the mapper function and the address of a file block co-located in the node. In this example, assume that 3 nodes are participating, namely Node 1, Node 2, and Node 3. Another simple principle around MapReduce is that the output of the mapper phase and the input and output of the reduction phase consist of a list of key-value pairs. This is such an important concept in MapReduce that it is worth putting it in the context of the example we are working with. In this example, a key would be the name Hadoop, Big Data, or GreenPlum, and the value would be the number of times the name appears in the file. After executing the mapper function, each node would produce a list of key-value pairs, where the key is either the name Hadoop, Big Data, or GreenPlum, and the value indicates the number of times that name appeared in the text. For example, the output for Node 1 could be Big Data 7, GreenPlum 5, Hadoop 4, while the output for Node 2 could be Big Data 9, GreenPlum 8, Hadoop 6, and the output for Node 3 could be Big Data 3, GreenPlum 4, Hadoop 9. We can then use the reduce phase to sum the results obtained by each node to reduce, get it, the output of the map functions to a single list of key-value pairs. In MapReduce, a node is selected to execute the reduce function. All other nodes need to send the key-value pair list created by the map function to the designated node. Assuming that node 2 in our example would be the designated reduce node, node 1 and node 3 would send their results to node 2. Typically, during the reduce phase, the entries are sorted and shuffled first before the reduction occurs. In our example, the input to reduce could be Big Data 7, GreenPlum 5, Hadoop 4 coming from node 1, Big Data 9, GreenPlum 8, Hadoop 6 already residing in the local disk on node 2, Big Data 3, GreenPlum 4, Hadoop 9 coming from node 3. And after sorting, where the key-value pairs with the same key have been grouped together, it would be Big Data 7, Big Data 9, Big Data 3, GreenPlum 5, GreenPlum 8, GreenPlum 4, Hadoop 4, Hadoop 6, Hadoop 9. and after shuffling where the key value pairs with the same key have been combined in one entry with a single key and a list of values, the result would be Big Data 793, GreenPlum 584, Hadoop 469. The reduce function then adds the values up for each key value pair, leading to the final result, Big Data 19, GreenPlum 17, Hadoop 19. In the MapReduce framework, both the mapper and the reduce operations are considered tasks, and the tasks together form a job. The MapReduce framework requires that a job tracker coordinates all the jobs run on the system by dividing the job into tasks and scheduling them to run on nodes. It also keeps track of all the nodes participating in a computation, monitor their status, orchestrate the data flow, and handle node failures. A number of task trackers run tasks and send progress reports to the job tracker. If a task fails, the job tracker can reschedule it on a different task tracker. The task tracker keeps track of all tasks running on its nodes, be it a map or reduce task. Similar to Hadoop distributed file system where a node assumes the role of a name node, in MapReduce a node assumes the role of a job tracker. Before running a job, a Hadoop programmer provides Hadoop MapReduce with the following information: the location of the data to be processed, which consists of a list of file blocks and the addresses for all its copies provided by the Hadoop distributed file system, a map function to be executed during the map phase, and a reduce function to be executed during the reduce phase. The programmer obtains, as a result, a list of key value pairs. You now have a simplified view of Hadoop mechanisms and the value it provides to big data. You just saw how the Hadoop distributed file system leveraged the cluster architecture to organize big data across hundreds or thousands of nodes, and how it is motivating us to think of computational tasks on big data as a set of tasks that can be executed in parallel across these nodes. In a way, Hadoop computations in a cluster architecture provide an extension to the typical computations done in an enterprise setting, enabling them to perform data-intensive analytics on big data. According to predictions done by Yahoo, by the second half of this decade, 50% of enterprise data will be processed and stored using Hadoop. With big data, the value is in the eyes of the data scientist, and he or she must have total freedom on the type of analysis performed, challenging us technologists to really think differently. So let us go out and take a thought leadership role and help our customers truly unlock the potential in front of them. Once again, EMC is strategically positioned to capitalize on this new paradigm. Learn more today about EMC GreenPlum, EMC Hadoop, EMC Isilon, and more. EMC technologies empower you to really harness the value of big data using Hadoop and more. We hope you enjoyed learning the simple principles behind Hadoop. As you heard earlier in the animation, Doug Cotton got the inspiration for Hadoop after reading Google papers on Google File System and Google's MapReduce. Google papers described a design that enabled the analysis of big data in the context of a cluster architecture. Google had to move to a different paradigm altogether because it wanted to use commodity hardware and because it was dealing with big data. In essence, big data processing is fundamentally data intensive, rendering the network as a potential bottleneck. Big data may be unstructured, making it impossible to organize the data based on the potential query and use of the data as it is done with SQL database. And big data analysis requires a different way of processing. It can be exploratory, where the question asked is not known prior to the analysis, and different hypotheses are examined, leading to additional explorations. It can be iterative, where processing may traverse the same data set multiple times, each time gaining a different insight on a different perspective of the data. It can be comprehensive, where the entire data set is analyzed, and it can be all of the above. We want to emphasize one of the main reasons why Hadoop is indeed a serious player in the context of big data. About 10 to 15 years ago, the volume of data being collected and the demand for analysis grew dramatically at web-related companies such as Google. The traditional way of storing and analyzing data on top of the single relational database management system and single process execution could not scale up at the same rate as data was growing. Something had to be done. An option was to use distributed processing to scale out despite the complexity involved in running in distributed processing systems. After a while, the time spent by developers on the mechanical aspects of distributed processing, managing servers, monitoring if tasks were concluded, reassigning tasks, and so on, was much greater than the time spent on the analytical part. Something needed to be done to make the mechanical aspects of the distributed processing automatic and the developers more productive. At this point, Google published the Google File System in 2002 and the MapReduce in 2004. During that time, Doug Cutton was leading the Apache Notch project, which was a web crawler. The idea of GFS and MapReduce were added to the Apache Notch project, which made it much broader than just a web crawler. Yahoo started contributing massively to the project. And because of its bigger scope and growth, the project had its name changed to Hadoop. As the ecosystem around Hadoop evolves, the complexity of dealing with distributed processing and distributed files will be more and more hidden from the users and developers. As a consequence, the adoption threshold will decrease and Hadoop will become increasingly popular. In summary, dealing with distributed processing is a necessary ill to tackle the rate with which data has been growing, given that scaling up cannot do the job and it is very costly. We hope you enjoyed this video, you learned from it, had some fun along the way, and hey, think big, think data, think big data.